This is my first video in a brief module we're going to do over using inverse trig functions in right triangle application type situations. But inverse trig functions which allow us to actually solve backwards for angles. Okay, so the first thing we're going to do is consider this triangle that I've got implanted in my canvas here. But this triangle here, we see that we have an angle theta down here. We're going to go ahead and assume that this is a right triangle, which is kind of an important feature. But given this right triangle, could we find this angle theta? And what I can tell you is, well, we know one angle is 90 degrees, but we don't know either of the two other angles. So, in a typical situation, if we didn't know these side lengths, we say, well, I wouldn't be able to find out what these other angles are. But the fact that this side over here is 3 and that the bottom side is 7 gives us at least a little bit of insight into what this angle might be here. Or at least what I can tell you is this: if the side over here had been 7 right here, if these were both 7, we could say then what we'd be dealing with would be like a 45, 45, 90 triangle, or at least I could tell you that this is 45 degrees. But the fact that this is only 3 compared to this 7 right here, at least we can say this: it's less than 45 degrees. Less than 45 degrees. The whole intent of this video, though, will not be to speculate as to what this angle might be, which we could get a good guess, but really just find exactly what this angle is. And a tool we can use to discover this would be what we call the inverse trig functions. Okay, so the first thing I want to do is actually this. Before we move into the inverse trig functions, I want to find out what relationship could we set up, or at least what trig function could we use to relate this unknown angle to these two sides of the triangle. And of course, if you're familiar with SOHCAHTOA, which I'm assuming that anybody who tunes into this is, we could say, well, with this angle right here, we could compare this opposite side to its adjacent side. And of course, opposite over adjacent, that would be our tangent function. So we could say tangent of this unknown angle is equal to 3 over 7. The simple fact is this: we are after this angle right here. And in an algebraic sense, if we had this equation, we say, well, what could I do to solve this equation? Well, I've seen everything being a teacher, including this. I've seen people even try to divide out the word tan, okay, from this and say, well, that would be my theta right there. But one thing I want to point out is that doesn't make any reasonable sense given that tangent is a function. That would be just like saying this: hey, mat divided by AT, the AT's cancel out and you're left with just MT, which would make also no reasonable sense. So here's the deal: we have to have something that is designed to undo the tangent function. We actually have something that undoes it. We refer to it as tangent inverse. Okay, so as far as the inverse trig functions go, I'm gonna back up here. I just want to get that out of there. I wanted to get this little circle down here so we could read this a little bit more easily. We say the 3 inverse trig functions are sine inverse, cosine inverse, and tangent inverse. You notice that we write this little -1 on the top corner. It doesn't mean that it's the reciprocal of sine, cosine, or tangent. It means that it is the inverse of those functions. Okay, so you'll notice also that I read these as sine inverse, cosine inverse, and tangent inverse. That is how they are read respectively. So we say they're sometimes called arc sine, arc cosine, arc tangent by the older math crowd, or anybody that's in, say, a pre-calculus or calculus sense. But these inverse functions have unique properties, and I've listed them below. But basically, what happens is this: if you were to take the sine inverse of, you'll notice that I say sine inverse of, I put a beginning parenthesis, of the sine of theta, okay, what happens is the sine inverse cancels out with my sine, and what I get left with is just the theta part of this. Or likewise, if I were to take the sine of the sine inverse of theta, the sine and the sine inverse cancel each other out, and you're left with just the theta part. Okay, so these functions here, and that's true for sine inverse. You could also use cosine inverse to undo cosine, or use tangent inverse to undo tangent, which we're going to do up top here. But essentially, that's what they're designed to do. So in our original sense up here, we said, well, we had an original equation. We said it was tangent of some unknown angle that we have down here we're trying to discover is equal to 3 over 7. Our job was to discover, well, what is theta then? What we're going to do then is this: we're going to take the tangent inverse of, notice this, a beginning parenthesis, of what? Of everything that was on the left here, which was tangent of theta. That should kill off our tangent on the left. But what you do to one side of an equation, you have to do to the right side. So we also have to do the tangent inverse of, and we're just going to drop in the value we had on the right side. So we say tangent inverse of 3/7, and here's instantly what happens. The tangent inverse and the tangent cancel out, and I'm left with this statement right here. We say theta is equal to the tangent inverse of 3 over 7. And what I want us to realize before we pull out our calculators and evaluate for this right here is this: that tangent inverse is the angle. The angle in inverse trig functions, they are the same thing. So when you look at inverse trig functions, they are literally saying I am an angle. And as a matter of fact, this right here, if I were to write in words, you say, actually, let me do this. I can type much faster than I can write, and it looks cleaner. We say, this says, we'll just do a contraction here. I'm the angle that has an opposite side of 3 and an adjacent side of 7. Another way to look at this is I'm the angle that when you take the tangent of me, you get 3 divided by 7. Okay, sorry that's kind of an off color there, that green. But basically, that's what this thing is saying right here. So what we want to do is we want to essentially say, well, what angle would it be that when you take the tangent of it, you get 3 over 7? And the nice nifty thing about it is this. All calculators are going to have inverse trig keys on them. So for instance, if I wanted to find tangent inverse of 3 divided by 7, this calculator is a little bit different. If I had a more scientific calculator, I could just type in literally tangent inverse 3 divided by 7 with an end parenthesis. But we're going to have to do this. We say 3 divided by 7. We're going to do that first, enter. And then I'm just going to hit tan inverse, which in this case, it looks like I'm going to have to shift. There's my shift key here. There it is, tan inverse. And so we click on this, and it says about 23.2-ish. Okay, and you notice that my calculator is in degrees mode, so 23.2-ish degrees. So once I discover this, I'm going to go write this back up here. We say this is approximately 23.2 degrees. And you should always ask about reasonability. Would that be a reasonable answer? Well, certainly that'd be reasonable. I mean, it's the smallest angle of the triangle, it seems, and it was opposite the shortest side length. And the nice thing about finding one angle in your triangle is, well, we could actually just use that angle to go find the other one, because this up here has to be complementary to this one. So this one up here would be 90 degrees. 90 degrees minus 23.2 degrees, which in our instance, get the calculator back out here, we say 90 minus 23.2-ish. We get 66.8, which is entirely reasonable as well. But that's because both of these angles, the acute angles in a right triangle, have to add up to be 90. So that is how we can use inverse trig functions to solve for unknown angles. That being said, let's just run through a couple of examples. Starting with this one here, it says use inverse trig functions and a calculator to solve for theta in the following equation. So we say sketch a picture of the triangle first. That is just a recommendation. As a matter of fact, we could just go solve this equation right now. If we say sine theta equals 3 over 10, then what we could instead do is just this. We'll undo sine using sine inverse. We'll do sine inverse of everything on the left, which was sine inverse of theta. We'll do sine inverse of everything on the right, which is 3 over 10. Okay, so we'd say, well, my sine inverse and my sine, those are designed to cancel out. And I'm left with this statement here. We say theta equals sine inverse of 3 over 10. But what I want to recall is this. We're saying this angle right here, this is saying this. I am the angles theta that when you take the sine of me, you get 3 over 10. So when I say sketch a picture of this, what I'm really advocating of us doing is this. We say, here's my right triangle. If I were to drop in our angle theta down here, what it's saying is when you take the sine of me, you get 3 over 10. Well, remember how you take the sine. SOHCAHTOA, say so, opposite over hypotenuse. What this means is the opposite side must be 3 and this side must be 10. We're really trying to answer this question, so what is the angle? Now, did I have to draw a picture? No, but I can tell you this, that actually gives me some insight as to what this might come out to be. And when I get my calculator out now, we say, okay, well, here's what I need to do. I need to do 3 divided by 10 on my calculator first. Enter, which is 0.3. And then we'll do sine inverse. We get about 17.5-ish. So I'm going to go ahead and put this up here. We say 17.5-ish degrees. Okay, it looks entirely reasonable. It's a very small angle, but then again, it was short, opposite the very shortest side. And then I want to solve for this angle up here as well. So this would be 90 degrees minus 17.5 degrees, which, asking our calculator here, if we were to just say subtract 90 from this and then call it positive, we get about a 72.5. Okay, so this is about a 72.5 degree angle, which is entirely reasonable. Okay, so the one thing I want to do before we sign off this video is this. When you evaluate on your calculator, it's really important when you're using inverse trig functions to have your mode on your calculator set into either degrees or radians, depending upon which you're looking for, whichever is desired, I write here. So it says, for the sake of these next expressions, what we're going to do is we're going to sketch a picture of the triangles, but then we're going to do these on the calculator, both in degrees and radians, and talk about the difference between the two situations. So we say, all right, let's start with this one here. Remember, this is some angle. When you talk about inverse trig functions, you're saying I in the angle. That when you take the cosine of me, you get 2 over 9. Remember, cosine, ka, is adjacent over hypotenuse. So what I'm going to do is I'm going to draw a triangle. It kind of looks like this. And I'm going to say, all right, well, I'm going to put my angle down here. And we know that when we take the cosine of this angle, adjacent over hypotenuse, we get 2 over 9. So this must be a kind of a larger angle right here. Okay. So like we said, we're going to get our calculator out. We're going to do this calculation here, this value here, both in degrees and in radians. So first things first, we say 2 divided by 9. This is a decimal, is 0.2 repeating. But we say, all right, well, cosine inverse of this, we say about a 77.16 degree angle. So we say theta is approximately 77.16 degrees. Now, this is when we did it in degrees, okay? 77.16 degrees, which looks very, very reasonable. If we were to now go back and calibrate our calculator to be in radians, which we could do this here. We say radians. Where's my radian? Oh, here it is. So you flip between radians and degrees. You see it's in radians mode. If we were to try this again, we say 2 divided by 9, enter, and then say, okay, well, I want to do now cosine inverse, which is what we were evaluating for here. We get 1.34, okay? We get 1.34 radians. And, keeping in mind that 3.14 rad, which is pi radians, it's really pi radians, is the same thing as 180 degrees. Well, 77.16 is roughly a third of 180. So if we were to do roughly a third of 3.14, just kind of speaking about ballpark figures here, divided by 3, it'd be around 1.04. So this figure we're getting here, about 1.34 radians, yeah, that's about right. Okay, that's very, very reasonable for what we're getting. Okay, so one more. I want to do tangent inverse of 1.424. And the thing is, like I said, I want to sketch a picture first. Remember, tangent is toa. So we have an angle that when we take the tangent of it here, we get 1.424. To make this into a ratio again, why don't we put this over 1? Okay, so what this means is I kind of have a triangle that maybe looks a little bit like this. Here's our right angle. Here's our angle theta. We're saying if I took the tangent of this, I would get 1.424, which is our opposite side, divided by 1, which we kind of planted in there, which is our adjacent side. This would be our situation. And so again, we'll do this on the calculator, but keep in mind, hey, if the opposite side's a little bit longer than the adjacent side, this angle must be maybe a little bit bigger than 45 degrees. So let's talk about what values we get. I'm going to flip back over to degrees, clear this out. We want a tangent inverse of 1.424. So 1.424, hit tangent inverse, we say about 54.9-ish. Okay, so we say theta in degrees is about 54.9 degrees. That's entirely reasonable. And if we wanted this in radians, hey, by the way, we could take this times pi over 180. It's just that our calculator does it for us. We'll just flip over to radians mode. And again, we say 1.424. We'll do the tangent inverse of this. We get 0.96 radians. 0.96 radians. Okay, cool. So that is how we use inverse trig functions to solve backwards for angles. Cheers.